I am sorry for the switching off of the mic.
This part primarily talks about fundamental and derived quantities. We are going to be starting from number 10, the 10th topic. Then we'll proceed upward to position and then continue to 9, the 9th topic. So the first thing we discussed is the fundamental and derived quantities. The fundamental and derived quantities. The fundamental quantities we defined as the basic quantities that are used to define all other quantities. They are the basic units that are used to define all other quantities. They cannot be described or defined by other quantities. We say they are the primary quantities. They are the primary quantities. Now, while the derived quantities are the ones that are defined by fundamental quantities. The fundamental quantities are just 7 in number, and they are the mass, the length, the time, the temperature, luminous intensity, current, ampere, current rather, and current, which is the unit is whose unit is ampere, and amount of substance whose unit is mole. So while the derived quantities are the ones that are gotten or defined by fundamental units through mathematical approaches, mathematical relationships. So for example, if you combine speed and distance and time by dividing distance by time, we get speed. So we could decide to also multiply mass and acceleration, and we will get force. Those are mathematical relationships between the fundamental quantities, or mathematical relationship between derived quantities themselves. And that is the way we come about derived units, derived quantities rather. And we have other ones such as density, which is mass over volume. We have forces or force, which is mass and acceleration. Then we have velocity. And we said the difference between speed and velocity is that speed is scalar, so it is distance over time, while velocity is vector, which is displacement over time. Displacement there is a vector quantity, while distance and speed is a scalar quantity. So we also have acceleration, pressure. Acceleration is also vector, pressure is scalar, moment or torque, momentum, and power. All of these are derived quantities that we get by mathematical relationships between derived quantities themselves, or mathematical relationship between fundamental quantities. We also have work done. So it is expedient to know the formulas of all of these derived quantities. Now, the units that we use to measure fundamental quantities are called fundamental units. The units we use in measuring fundamental quantities are called fundamental units. So for example, the unit of mass is kilogram. We also have grams, but we are going to be using the SI units. That is the standard international unit. So that of mass is kilogram, that of length is meters, that of meter, that of time is seconds. Seconds. Then that of temperature is Kelvin. We also have degree Celsius, which we use, degree Fahrenheit, degree, and we also have Rankine. So, but the SI unit of temperature is Kelvin. We talked about degrees Celsius, which is also called degrees centigrade. Degrees centigrade. So we also have luminous intensity, whose unit is candela. Luminous intensity, the unit is candela. Then a magnetic flux is not a fundamental quantity. All right. So we said acceleration is what? Velocity over time. And we have already gotten velocity to be L t raised to the power minus 1. We don't have to do that again, but if you want us to do that, we can redo it. Velocity is displacement over time over this time. Is that okay? So what that is saying is just, this one will come down. I've told you, if you are dividing a fraction by a whole number, just bring down the denominator to become L over t times t. That becomes L over t squared, which is equal to what? L to raised to the power minus 2. In units, length is meters, right? Time is seconds, right? Let's minus 2, that's the answer. So for the next one, pressure. No, let's analyze force first. What's the formula for force? Mass times acceleration, right? Now, what is the direction of the acceleration of a body? The direction of acceleration of a body is always towards the force that causes the acceleration. Keep that in mind. The direction of acceleration is always towards what? And this is what I mean. So you might be thinking that if force is coming like this, where will the body move? If I punch something like this, where will the body go? That direction. Is that okay? The direction of the force. Does that make sense? Okay. And acceleration is vector. This guy is scalar, vector, 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 scalar. All scalars. So as we are mentioning now. Alright, so for this guy, mass corresponds to m, right? It's because acceleration, we've done acceleration here, right? Times L to the power minus 2. So it means our guy is mlt to minus 2. Then the unit is going to be what? kg meter per second squared, right? Which corresponds to what? Newton. Does that make sense? Because Newton is the unit of force, right? So Newton, this is the standard unit of, no, this is SI unit, but like I'm saying, the dimension for Newton, this is it. And of course, you can break down all types of forces to this. You know, that's what I said I was going to show you in when we did gravitational force, all those forces. You can always, those formulas, you can always break them down back to this. Anyways, the next one is number 3, which is pressure. Pressure, right? Okay, so what's the formula for pressure? Force over area. What is the formula for force? M L T raised to the power minus. We can write this as ML over T squared, right? This force here. Is this clear? Yes, sir. This force now. Or if it's confusing you, ML T raised to the power minus 2 might be more confusing. That's why. Okay, over, what is area? L squared. Okay, this will now become ML T raised to the power minus 2 over length squared is length times length, right? L takes care of L. Now M, L is under, that will be L raised to the power minus 1. T is still raised to the power minus 2. Does this make sense? But for the sake of next time, because there might be some now that we have to cancel something from this T. So in such cases, I could just bring this guy as ML over T squared. This is what corresponds. Do you understand now? So we now have so divided by L squared. This now becomes ML over, when you're dividing by a whole number, you bring this one down and multiply. Is that okay? Yeah, takes care of 1, then we now have ML raised to the power minus 1, T raised to the power minus 2. You see it's the same now. Alright, let's go to the next one. What's the next one there? Moment. So if I said analyze moment, very simple. First, know the formula. The formula for moment is moment of force. It's going to be what? Force times distance. Well, you must have seen in some textbooks where you are calculating with mass. You now say mass times distance in clockwise direction is going to be mass times distance in anti-clockwise direction. The reason is because it's still force we are using, the weight of the body. Is that okay? But why we always eyeball G is because mg here, D. G will still be constant here, right? So mass might change. So you now cancel mg G out. Do you understand? But moment is what? Force times distance. Don't let that confuse you. Is that okay? Force times distance. Distance. And force, we got it to what? ml over t squared. Isn't it? ml to the power minus 2. So times, distance is L. Okay? Distance is length. So that becomes ml squared t to the power minus 2. Okay? The next one is what? What's the next guy there to be analyzed? Momentum. Okay, number 5 is momentum. Now, okay, the difference between moment and momentum is torque and momentum is just torque is in a circular direction. Is that okay? And moment about we call it a turning moment. That's a torque. Is that okay? A turning moment. Okay. All right. So, but of course, even moment we turn, so they are basically the same. Is that okay? And of course, the unit does not change. So, what will be the unit of this guy? Mass. That's kg meter squared per second squared. Good. What's momentum? Momentum is mass times velocity, and it's denoted by p, right? Okay. So, mass times velocity, that is mass times velocity. And mass is m, so we have m times what velocity? L to the power minus 1, right? So that becomes ml to the power minus 1. You see that I'm interchanging my writing. I'm putting m times l over t. This guy is the same as this. You know that, right? Okay. So this becomes kg meters per seconds. All right. Let's go to the next one. What's the next one? Impulse, right? Power. Now let's analyze work done before we analyze power. What's work done? Mass times acceleration, just wait, times distance, right? So what do you see? Mass and acceleration, force, right? Distance. So it basically means that they will have the same dimension. So moment and work done will have the same dimension, but they are different. Work done is what? Scalar. Moment is what? Vector. Don't forget to, when you get to vectors and scalars, I'll give you that mnemonic. But work done is scalar, this guy is vector. Another difference is that work done is just work done, force acting over a given distance. They're basically the same, but this one has to be turning effect. Is that okay? All right. So we have done work done basically. That's what it means. Then what's now power? What's power? Time rate of work done over time. And what is work done? ml squared over t squared. Is this one clear? Okay. Then over t. So that means that t will now come down. T will come here. Does that make sense? Okay. Please understand the math. So if you don't understand the math, let me know. Over t raised to power 3. So power becomes what? ml raised to power 2 t raised to power minus 3. Am I correct? Are you sure? Okay, then the next one, which will be the last, is impulse, right? So what is impulse? Impulse is rate of change of velocity, right? Which is force times time, right? So what is force? ml over t squared times t. T will take care of 1t, then we have ml over t. This becomes what? ml t raised to power minus 1. So this becomes kg meter per seconds. And here, kg meter squared seconds raised to power minus 3. Do you understand now? All right, so this is everything about dimension analysis. Let's go to the next topic, which is what? Position, distance, and viscosity. Have you started it? Yes. Good day, the chairman. Panel of judges. Really? Okay, let's go, please. Position. Now, position is the location of a thing at a particular time. Is that okay? So position has to do with time too. It's time dependent. So meaning that's why we define motion. So we have to actually talk about motion soon. After position, what are we supposed to do? Motion, right? Motion. So what is motion? Change in position of with time, with respect to time. Is that okay? So that's why position is related with time. So and we represent position using the Cartesian coordinates. Coordinates now, XY coordinates on the Cartesian plane. So if I say the position of a body is point A, and I say what is point A? Point A, you told me, is at 3, minus 2. How do we identify this in the position on the Cartesian. So what you do is you draw your graph. So you have origin 1, 2, 3, 4, 5. Here, -1, -2, -3. Here, 1, 2, 3, 4. Here, -1, -2, -3, -4. Okay, let's stop here. So it now says the position of a body is at point A, which has the coordinates 3, -2. 3, -2. So the first letter here represents your first x. It's written like this. It's written x, y. Is that okay? So this is a point on the Cartesian. So your first x is going to be 3. Your first y is going to be what? -2. So your first x will be 3. Let's go to 3. This is 3, right? We're not marking it. 3. Then our y is -2, right? So now trace it down to -2. This is -2 here. So where they meet, their point of intersection is our position. So this point A. Is that okay now? All right, I can use that to do many things. So, but now let's go to distance. What is distance? So basically, there's no question that you probably might get under here that you cannot. All you just have to do is, if they give you different points, and just chart it out, create a graph or something, find the slope. Those are the possible questions there. Is that okay? But of course, you don't even need to chart anything. If you are given like 2 points now, and I'll say what is the velocity of the body, you know that velocity of the body is in position. Okay, good. Now this will be position time graph. In position and time, position with respect to the time, the slope of the graph will give us velocity, while the slope of velocity graph will give us acceleration. Does that make sense? Get that too. The slope of velocity position time graph will give us what? Velocity. While the slope of velocity time graph will give us what? Acceleration. Okay. So those are the possible things. So how do we take slope? Slope in maths represented by m is equal to y2 minus y1 over x2 minus x1. I saw you said you didn't know something about this also. Okay. Anyways, so that's it. Just take your x2. Let's say we're given another coordinate, point B, which was on the coordinate 4, 5, 3. For example, let's use 3, 4. No, 2, 4. No, -2, 4. All right. So what that is saying is we have -2, 4. So on x, so what -2, then 4 on y. That's around here, right? So when we have to join it, we just join it. Honestly, just because today is Monday. Okay. Let's see now. Something like it now, something like it. So when I take the slope of this thing, just do it like this. The slope of this line is going to be y2, which is this. These are x2, y2. Is that okay? Second y-axis. So that becomes 4 minus x1, y1 rather, -2 over x2, -2 minus x1, 3, becomes this plus this, 6 over minus this, 5. So the answer is what? Minus 1.5. Is that 1.2 rather? Is that okay? By the time you solve that. So that is how to check for the velocity, which will be the slope of the position time graph. Okay, so now what is distance? So distance will now say, find the distance between these 2 points. You can use anything to do that. You can use Pythagoras theorem. You can use distance. After knowing, if you are given the speed now, you can take the distance. If you know the time from here to here, you know this was position against time. Is that okay? So if you are given that, you can, what do? And you are given the speed, or you have gotten the speed, you can check the distance, because speed is equal to what? Distance over time. So distance will be equal to what? Speed times time. Is it clear? All right. Or you can use Pythagoras theorem too. Hypotenuse square is equal to what? Opposite square plus adjacent square. Either ways you want to go about it, you get the same answer. So that's what distance is. Let's take a question on that. This question says, a body moving with a constant velocity. Please pause it. Let me take time to quickly write it. It's here, so I can be close to this thing, please. Let's go, please. A body moves with a constant velocity along a straight line ABC. There's a straight line. Oh, it's bleeding. A straight line ABC, right? A here, B here, C here. It takes 45 minutes to go from A to B. So from A to B, it takes 45 minutes. And from B to C, 10 minutes. So it means A to B must be longer. Does that make sense? So from here to here, it took 45 minutes. And here to here, it took what? 10 minutes. It now says if AC is 3 kilometers, from here to here is 3 kilometers. Okay? Now let's put it here on top. So from here to here, 3 kilometers. Okay? So how do we calculate? Find AB, find the distance from here to here. Very simple, it's just like division of line. But basically, since it's a straight line, we can easily calculate as this. You know that the total distance, what's the total distance? 3 kilometers, right? Total distance is 3 kilometers. So let's calculate the speed with which it traveled throughout the entire thing. So average speed you cover is going to be what? Yes, sir. Total distance traveled over total time taken. What's total distance traveled? 3 kilometers. What's total time it took? 45 plus 10. How about 55? So I will have to use the standard unit. What's the unit of this? Standard unit of distance. Meters, right? That will be 3,000 meters. That's kilometer. This is 3 kilometer. Kilo means 1,000, right? The time, yeah, the time too. Minute to change to seconds, so that will be 55 minutes times 60. 55 times 60 is what? 3300 seconds. Is that okay? So this now becomes 0000. 30 divided by 33. Roughly 0.91, right? Meters per second. So this is the speed of the body throughout the entire race. More like it's traveling 1 meter per second for what you're seeing here. Is that okay? But the question says we should find the distance AB. This way is to put line AB. So I supposed to write from here to here. We have known the speed that it took over the entire thing. So since speed is still distance over time. Now we're looking for the distance AB over the time over which it took. 45 minutes. What's 45 minutes? 45 times 60 is what? 2,700 equal to the speed that it took through that distance. Is 0.91. So AB is going to what? This times this, which is what? 2,000 what?
2,450.
2,430.
223,000.
What is this saying? 0.91 times 2,700. That's just more like 1 times this. Should give you something very just less. 2,430. Is it 457?
It's 247.
2,457 meters. Is that okay? In kilometers, that will be 2.457 kilometers. And that makes sense because that's the longest distance here. If it's 3 kilometers, that's the longest. Are we good? All right, will you calculate this one for me? Just start it out. It's very simple. This one says a man walks. Stop writing and listen. A man walks 3 kilometers due east. Where is east? Here, right? No, where is east? Is this east? Yes. You must know it though. Is that okay? Where is west? West.
This side. It's down. Yeah, it's down. This side.
I will send you a knock now. So where is south? Where is north? Okay. So we now have due east, and then so from here to here is 3 kilometers. Now you have to use common sense to draw the next one. It says 2 kilometers due north. It must not be as long as this, right? This is like 2 kilometers due north, around here, right? 2 kilometers. So what will be the displacement? You draw this line. Is that okay? This line represents the resultant is the displacement. Is that okay? So this is the displacement. You now say, okay, you now say find the displacement. This is 2 kilometers. So fastest finger, let's hit.
3.6.
Calculate the resultant. So the resultant is going to be, which is the displacement in a specific direction, right? What's this called? H, right? H, yeah. H squared is equal to what? And that's 2 squared plus 3 squared. That becomes 4 squared plus 9 squared. That's what? So H equals square root of 13. What does that become? 3.6 what? Exactly 6. So 3.6 and 3.6 will give you 13. Square root of 13. Let me see. Okay, that's good. Really? 605 now. 605. Be careful to approximate anyhow, eh? So this is this guy. The distance he has moved resultantly. Is that okay? But what will be his direction? So his direction is going to be tan theta is going to be opposite, which is 2 over adjacent. So that becomes theta is going to be the tan inverse of 0.661. So theta is going to be what? 0.7283. Tan inverse of this now. 0.7. No, now. Theta is going to be tan inverse of this is what? 3.43. 33.46 degrees. Is that okay? So this will now be, in what direction would this be? It's going north and east. That what? Northeast. Does that make sense? So his direction will be, it will be 3.6 kilometer, 33.46 degrees northeast. Is it clear? Are you sure? Alright, the next one. Now let's go to motion, friction, and circular motion. Yes? Another question on this? Have you gotten a question on motion, on displacement? I told you to be looking for those. So what did we define motion as? The change in position of body with time. Alright, and there are different types of motion, which are what? We have what? Circular here, relative here, oscillatory, random. You're not talking. What did you not say? Translational here. I'm not in for translational motion. Linear motion, yeah. Translational or linear motion. Or rectilinear. Is that okay? What again? Rotational. So you know that circular motion is from rotational, right? So for rotational, it's about a fixed point, right? So there's a fixed point and then we are going around it. While circular motion is the entire body is displaced in the circular path, right? And so the difference is that one is a regular circle, the other might not be a regular circle, might not be a perfect circle. Is that okay? But they behave almost the same way. Is that okay? Alright, so we have relative. Relative motion is motion of a body due to the movement of another body, or relationship between two moving bodies. Is that okay? That's relative motion. Is that okay? Do you remember when I was telling you about the fact that if you were running and a car passed beside you at a higher speed, the speed will not be as much as when you are standing. If you are standing still, because that car is moving relative to you, your own velocity there is zero. His speed will be very fast. It will look faster than if you were actually running. Do you understand that now? All right. So the oscillatory motion is just to and fro movement. Any repeated motion. That's what? Oscillatory motion. Random, haphazard movement, right? Now we talked about Brownian motion. So gases engage in what kind of motion? What kind of motion? Brownian motion. It was named after who? Can't remember. Brown something. I think James. James Brown. No, not James Brown. Okay, translational motion or linear motion. What's translational motion? Motion on a plane, right? On a straight line and on a plane, of course. So, but of course, we know that it could involve to and fro too. But basically, it's just as far as it's happening on a straight line on a plane. So it's translational. Is that okay? Data. A tire. Yeah. So it's a tire has. So we have the wheel and the axle, right? The wheel, the tire, and the axle. So we have something like this. How do you draw tire now? Come down. No, tires must have drawing. Okay. Just come down. Are you okay? So this will now have an axle projecting outwards. No, if you are looking at this side, it means the axle is projecting from. Are you with me? So this is the wheel, this is the axle. Is that okay? The one that joins those two guys, right? So now the axle, more like the rim. Is that okay? You know the rim is attached to it. So this tire is going to be engaging in what? No, the axle, this axle first is going to engage in what? Translational motion. Is moving, right? But this guy is rotating about this thing. So it's going to be engaging in what? Rotational circular. Rotational motion. Do you understand now? Because it's moving about this axle. That's why it's called axis. Is that okay? Then the entire body of the car, if it was going in a roundabout, what kind of motion would that be? Circular motion. But the two, this guy is still going translational, while this guy is still going rotational. All right. Okay, let's go to the next thing. So that now let's discuss friction. Now, if the body was moving in a friction, so a rough surface. So what is friction? There's a force that acts between the surface of that object and the surface itself. So what is that force called? Friction. So we call friction a force that does what? Opposes motion. In my GS class, I think I remember my teacher said, friction is a force that tries to oppose two bodies that opposes two bodies that are trying to move over each other. I'm sorry. So I shouldn't know that definition. But the point is this: that when two bodies try to slide over each other, there's going to be a force that is impeding motion. Is that okay? So that resistance to motion is called what? Friction. It has advantages, right? What are the advantages of friction? Brake in cars, yes. Vehicles, yeah. It's able to walk. In fact, the reason I'm able to stand and walk without sliding is because of what? Friction between the sole of my feet and the surface. All right. What again? Well, that's the advantages, right? Causes wear and tear of moving parts. All right. Then how do we reduce friction? Greasing, right? How about use of rollers? Do you know use of rollers? Yes, rollers tires also reduce friction. ball bearing. See, roller is, for example, I want this thing now to go towards you. I can slide it like this, but you see, it will soon stop because of friction. But if I put rollers here, if I put this thing like that, something that can roll, that has round body to move over that thing, easily. Is that okay? Seamless. Okay. There's also friction in air. Is that okay? We call it drag. We call it what? Drag. And it's also a vector. Air drag is also a what? Vector. Okay. How does it happen? If you throw a body, if I project this body, one of the reasons why it will not go its highest distance. Number one, we know that gravity is acting on it, but this thing should actually continue in that motion, if not for air resistance. Is that okay? That is why if I threw this body towards you, this thing towards you, it might not meet you. Unlike if I stone you with this thing. You know, right? Yeah, because the reason why is because this thing has a larger surface area, so drag is plenty on it. But this thing can protrude the air. Is that okay? Can pierce through the air. Do you understand? Alright. You don't understand? That's why the bodies of aircraft are designed in such a way as to minimize air drag. Are you listening to me? Yes, sir. We call their body, what kind of shape do we call their body? Yes, torpedo shape or streamlined. Torpedo shape or what? Streamlined. Or we call it streamlining. Another way okay, there's something called, now let's get to types of forces. We'll get to circular motion. Okay. So now friction. So for frictions, let's discuss questions. Okay. Now there's something you should know. Fish. Yes, fishes have streamlined body because there's also drag inside water. That's why they have that shape. This is torpedo shape. Torpedo. Somebody say torpedo. 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 In fact, they have a kind of tail that is called homocecal. Homocecal tail. Homocecal tail is the tail that allows them to run, to move very speedily. Any fish that has this forked shape for the tail is going to move very fast. So this is a streamlined body, this torpedo shape. This is the shape of an aeroplane, basically, isn't it? Of a bird too. Have you seen some birds? If you want to fly speedily, they will put their this thing together and move to be able to protrude, pierce the air. Do you understand? The one that I was flying. Yes. Number 2. Is that when a brick is taken from the Earth's surface? When a brick is taken from the Earth's surface to the moon, its mass dash. Number 1, we are not even there. Anyways, let's reason it together. When you take a brick to the moon, what happens? It said its mass dash. A remains constant, B reduces, C increases, D becomes 0. Nothing affects mass. It's weight that will reduce because acceleration to gravity in the moon is 1/6 that of Earth, right? That becomes 1.6, right? So it means that if the mass was 10 kg, 10 kg times 1.6 is going to be 16 Newton. But if it was on Earth, that body, which was 10 kg, on Earth will weigh 10 times 10, that was 100 Newton. So it's the weight of the body that's affected when, not the mass. Is that okay? Why? Mass is the quantity of matter in a substance. What reduces the quantity of matter? Nothing, right? Except you break it. Do you understand? All right. But let's not digress again. Let's continue what we're doing. Is that okay? I told you to get me questions on what we are doing now. We're getting to it now. All right. So I said friction. What happens to friction? Friction is the force that tries to stop body that from moving over each other. And we talked about the fact that there are 2 types of. Okay, now, no, not that. Now look at this body. Look at this body. Are you with me? Now, this body on this surface, there are 2 forces acting upon it, right? There's a force acting downwards from the center of gravity, right? What is that force called? Weight of the body. And it's called what? mg, right? But there's another force that is acting between this surface and this surface. It's called what? Normal reaction. It's called what? Normal reaction always acts between the bottom of the body, this base, and the surface of the plane on which is sitting. Is that okay? All right. So normal reaction is acting upward. Any convention you use is either N or R, but I prefer to use R. Is that okay? Now, for this body to move, the body is going to move if a body moves first. First, what creates acceleration? We say unbalanced forces. It's not just force. If there are more than one, yes, force creates acceleration. But if there are more than one force that's acting on a body, the body will move. Is that okay? I will now say it's unbalanced forces that create acceleration. Because now the reason why this body will not move and why it's not pushing into the earth is that R is exactly equal to what? W here. The normal reaction that the body is feeling, you soon become the chairman of that office now, is equal to the weight that is pushing down on the earth. So that's why this thing will not enter the earth, but to remain on this surface. Is that okay? Normal reaction equal to what? Weight. Please let's get this very clearly. Is that okay? But now, there is now a form of imbalance if forces are now acting on that body or inclined planes. I'm going to talk about inclined planes soon. But look at this body now. If a force was pushing down here, now we know that normal reaction equates weight, so nothing happens. Raise your head. So if there was an F in this left direction, F sub L, and there's another F that is pulling on this body, F sub R, in this direction. For this body to move, what must have happened? If F sub L is equal to F sub R, will this body move? If F sub L is greater than F sub R, in which direction will this body move? F sub R, right? F sub L direction. Because now if this was 100 Newton and this was 80 Newtons, this guy is going to move in this direction by a force of what? 20 Newton. Does that make sense? So the amount of acceleration that this guy can produce, this 20 Newton can produce, is what acceleration this guy will move with. Does that make sense? All right. But if the surfaces were off, there's also going to be a force that is assisting this force here. This is going to be what? Frictional force. Do we understand now? Now, frictional force is given by the formula F sub R. Frictional force, this is of F in right direction. Frictional force is given by coefficient of friction times R. There are two types of coefficient of friction. Mu sub S is called coefficient of static friction. Is that okay? And mu sub K is coefficient of kinetic friction. But for the purpose of JAM, we're just talking about mu without mu sub anything. Is that okay? Coefficient of static friction is for a body that is stationary. And coefficient of kinetic friction is coefficient of friction for a body that is what? Moving. Are you with me? All right now. So let's master these formulas and let's go on with it. So you already know how acceleration is created, right? Okay. So we now said that F is equal to mu R for frictional force. Now for a body in an inclined plane on a ramp, we have done a lot of ramps, right? So we don't have any problem with ramps. I'm going to use the easiest way, and of course we also go by the other methods. So M here, mass, weight of the body. Now in what direction should this body naturally move? Downward, right? Good. Now the force that is acting down, now but there is a force that is acting straight downwards, right? What do you call that force? Weight of the body always acts straight downwards. Straight downwards, not you don't trace the distance. The force that acts perpendicular to the surface will what? Normal reaction. So that one is going to act in this direction. Normal reaction. But what will be the value of normal reaction? The value of normal reaction is going to be, now this angle here, this ramp is inclined at an angle theta. By mathematics, we know that here is also what? Theta. If you don't know how to derive it, I'm going to link a video in the description that explains that. I cannot begin to derive that for you again. But theta here is going to be theta here. Is that okay? Now, in order to know the value of this guy, the value of this R, let's resolve this guy because we know that they will balance out, right? Mg is not equal to R here. In fact, know that Mg here is greater than R. The weight of the body is greater than what? Because R is acting perpendicular to this surface. And by the time you resolve this force to be perpendicular to this surface, what will happen? It will reduce the value. Is that okay? And anytime you are closing an angle, we say you are what? cos. You are opening an angle, you use what? Sine. So we want to close this angle here, right? So here, R will be equal to what? mg cos theta. Or the force acting in the opposite direction to R here, which we know will be equal to R, right? With what? mg cos theta. All we did was just to resolve this force in this direction. Is that clear? Okay. Who is not clear on this? Okay. So we know that R is m cos theta. Now, there's a force that is going to pull this body down here without us even having to interfere anyhow. So the force that will try to pull this body down is going to be what? The force that is going to move this body down is going to be what? Now we will now resolve this guy in this direction, because this looks like 90 degrees, right? So we'll resolve this guy in this direction. What are we doing to this angle by resolving this guy in this direction? Help me, right? So that becomes mg sine theta. So that's the force acting downward. Does that make sense? So it therefore means that if now there's going to be a force that is going to act if this surface were rough. Now, this inclined plane now we are assuming is smooth. But if it were rough, you know frictional force will act on it, right? So frictional force is going to act in the opposite direction. Is that okay? And frictional force, do you believe with me that it will also be mg sine theta? Because it means that if we resolve this guy here in this direction, it gave us mg cosine theta. It means any force that is acting parallel to the surface of this thing is going to be what? Mg sine theta. But this one is going to be negative mg sine theta if we were considering this as positive. Does that make sense? Are you with me? Why would this guy be positive? In a case where this guy actually slides down. So this guy will be positive, then to know the force by which this guy moved down. So MA on this body, I've told you how to resolve this before, is going to be what? Minus FR plus mg sine theta. Does this make sense? Or you say MA, or this body is going to move down with an acceleration that is equal to this mg sine theta minus f sub r. Is this clear? All right. Provided that but FR also is going to be mg sine theta. Now the only difference is this. You'll be given the coefficient of friction in this case for this body. Is that okay? So it's going to, so this value here is going to affect, this value here is going to affect the value that the friction takes. Is that okay? So that F sub R is going to be mu R. Is that okay? So in such case as this, then F sub R, we'll be given the coefficient of static friction. And the coefficient of static friction, because mu here is going to be FR over R, right? And both of them are Newton. Coefficient of static friction will not have any unit. Does that make sense? So F sub R, we said, will also be mg sine theta, right? Because it's also parallel to the surface, which we equal to this, right? Over R, and R is what? Mg cos theta. Does that make sense? So it therefore means that if mg cancels mg, then we can have what? That mu is also equal to what? Sine theta over cos theta, which is equal to what? Tan theta. Does this make sense? This is another way to get mu. You just be giving an angle. They say find the coefficient of static friction. Just say tan theta. Is it clear? All right. Another thing we should know. Now let's go on to solving the question. Look at this question. This first question says that an inclined plane at angle 30 degrees. Let me just draw it for you, so you solve it. Are you going to attempt it first, or I should attempt one first for you? Okay. This body is 120 Newton. Angle 30 granite. It now says, calculate the force parallel to the plane required to push a load of 120 Newton. Calculate the force parallel to the plane required to push a load of 20 Newton. Let's do it together. It's very simple. Let's do it together. Up the plane. That's what it says. Oh. A load of 120 uniformly up the plane. So there's something that you must notice. Since the load must move up the plane, what does that mean? That force must be greater than the force that must be greater than mg sine theta. Is it clear? Do you even get it at all?
Yes.
Are you sure? You did not get it? Okay. But so the first thing we should get is the coefficient of static friction. Let's first get the coefficient of static friction. You know that F will be equal to, now F is going to be the force now that is moving off the plane. Is that okay? It's going to be mu. Coefficient of static friction mu is going to be what? F over R. And what is F here? 120 over, oh sorry, F now we have mg, sorry, mg what? Sine theta over, no, would this be the force or frictional force basically? This will be frictional force, not the force yet. But of course, we know there is also a force here that is pulling in this direction. So what would this one be? Mg cos theta. And this one is already given as, the force is given as 120 sine 30 over 120 cos 30. Solve this. Sine 30 over cos 30. Tan 30, just do tan 30. 0.58. So mu is equal to 0.58. Now. It now says you calculate the force that is required to pull the load upstairs, right? Parallel to the plane, the force that can pull it up. Okay? It means that if a force can pull it up, it means that the force must be, how do you say? So calculate the force that is required to just push the load. To just push the load. Whenever you hear the word just, there, it means the force must be the sum of some forces there. Sum of some forces means that it must overcome those other forces. Does that make sense to you? Is it clear? It says that will just push the load. So it means that this force that must just push the load must be able to overcome the weight of the body. Okay, but the weight now is going to be tending, the weight is affected by this ramp system, right? So the weight is going to be the normal reaction. The weight will be equal to the normal reaction. Are you with me? Plus the force that is trying to push it down. Does that make sense? That the force that is able to just move that load up this thing must be the sum of the normal reaction. We cannot use ordinary weights here. Do you know why? Because weight is mg, is supposed to is acting downward, but there's an incline. Do you notice also that if you incline something, the ease of push of drawing on this surface will be different from when I slant this thing. So that's why we are using R, which is now mg cos theta, plus the weight that is the force that is pushing it down, which is mg sine theta. So what will R be here? Mg cos theta plus mg sine theta. Does that make sense? Are you with me?
Yes, sir.
Or is it this thing? You know also that frictional force okay. Coupled with frictional force. You know friction is also opposed motion. Does that make sense? Coupled with frictional force. So this here, the force acting downward here is not just going to be, so let's call it Fr. Does that make sense? So that the force here is going to be, Fr here is going to be F is equal to let's pause it. This motion downwards will be equal to this F minus the force in the other direction, mg sine theta. So by the time you do this, this guy will come here. Is this one clear? Should I explain? Should I explain? I said that frictional force here. Where's frictional for this body? For this body now, we know that this force is winning. Is that okay? But for this body, where should the body naturally slide? Downwards, right? Okay. So it's sliding downward by an amount, which is mg sine theta, right? And this force here is the one winning, which is the direction of motion. So to know the sum of forces acting on it, which is going to be the frictional force here, the net force will be the frictional force, or the force that is remaining. So that will be the force that is leading, which is in direction of motion. Any force that is in direction of motion must be what? Positive. Does that make sense? So, but this force, mg is acting downward, so it's against the direction of motion, so it will be what? Negative. Does this make sense now? So that will be frictional force. So that the force will now be equal to what? Frictional force plus mg sine theta. Is this clear now? So what's now frictional force? Mu r. In fact, that's the best approach to it. Have you played it? Oh no. Okay, played it. Okay. So this is the best approach. When you see, just try to get sum of forces, net force. Get the net force. On this system, all the forces acting on it is one is acting this direction, one is acting downward direction, right? So the frictional force, which should not be the net force, provided this surface is rough. I mean, since we are giving a surface like this, a ramp system like this, sometimes we have, except if you see is written neglecting friction. Is that okay? If you are told to neglect friction, then you can now solve in another way. But here, we know that friction will actually act. So the net force on this body, if one body is pulling down, the other body is pulling down, the net force on this body is going to what? Net force. But we know that the net force is going to be frictional force, and the force that is leading is this one in this direction, right? So any force in the direction of motion, where this body will move, is going to be positive, right? So the net force, which is frictional force, or the remaining force, do you understand now? Is going to be the force that leads minus the force that is not in direction of motion, which is acting downward. So to now get this force that leads, is going to be frictional force plus mg sine theta. And frictional force is mu r, right? So what is mu? Mu is equal to, mu r is going to be mg, what is r? Mg cos theta plus mg sine theta. So now, okay, we're not deriving the equation. We are solving, right? So that becomes 0.58 times, what is mg? Mg 120, right? Times cos theta. What's theta? 30 plus mg 120 sine theta times 0.5, that's 60, right? 60 plus, so do this. 120 cos theta times 0.5, 60.20 plus 60, 27, 28. So that becomes 120.28. Is it correct? Is this correct? 0.58 times 120 times cos. So this is the net force required to just move it up the plane, which will be greater than this, because this one will not necessarily, okay, it's to just move, right? And so maybe it's okay. Is that okay? So to move by an acceleration provided by 0.28 Newton. Does that make sense? Because that's the weight of the body, 120 Newton. Is it clear? All right. So let's attempt another one. Another one says, look at this one now. There's a force, now right. The diagram above shows a body. A body is resting on an inclined plane. If the body slides down the plane, so which force, if the body slides down the plane, which force is greater, or which force wins? Mg sine theta, God bless you. So here now, a force is now acting in this direction, 25 Newton. Then the mass of the body is 15 kg. So solve for what is the acceleration of the body. Calculate the acceleration of the body. Fast. Pause it, please. Are you? All right. So listen now. So what's the mass of this body? 15 kg, right? So we know that unbalanced forces create acceleration, right? So this body is going to accelerate down the plane with a particular amount of acceleration, right? But first, there are two forces acting on this body. The force acting downward, mg sine theta, right? And the other force, 25 Newton. Which one is positive in both of them? Mg sine theta. Because one is against motion. So it means that the net force, are you with me now? You see the way I'm analyzing it. Net force is going to be this force, mg sine theta minus 25. And net force is going to be mass times acceleration is equal to mg sine theta minus 25. So this becomes m, which is 15 times a, is equal to m times 10. You'll be given, I don't know if you was given the question, 10 meters per second squared. So that will be 150 sine 30 minus 25. 75 minus 25 is equal to 15a. So 15a is equal to 50. A is equal to 3 points. Divided by, that will be 3 over 5. That will be 1 over 3. That's 3 meters per second squared. Are we clear? You see, it's simple, right? Are we good? Okay, try this one for me. It says a body of mass 40 kg is lying in an inclined plane of slope 30 degrees and it is on point of slipping down. It's on point of, so it's going to slide down. That's what they are saying. So what is the force? What force applied to the plane will cause the body to begin to move up? That is, to just move up. Does that make sense? All right. So calculate it. So it's just like the former one we did. Take G to be 10 meters per second squared. Pause it. So there's a force that essentially calculate the force that we just need to push this body up the plane, right? So which we call maybe our F net, for example, as we use there, right? So F net is going to be equal to, first, there are two forces that are acting on this body, and those, for this body to move, it means the forces are unbalanced, right? So the first force here is the force that is in this direction. Does that make sense? The force in this direction, which is the direction we want to pull it. That force is in direction of motion, so it will be positive. F. Exactly. Okay. Now, there is another force we know is acting downward because of the slope of that thing. We call that force the mg sine theta, right? But motion is not downward, so it means that force is negative. Is this clear? Is this clear? All right. So, but we know that friction is acting on this surface, right? So it means our remaining force, which is F net, is going to be what? Frictional force. Does this make sense? Equal to F minus mg sine theta. But which force are we looking for? This force that is required to push the body up the plane, right? So that becomes, this guy will now go there. Fr plus mg sine theta is equal to F. So Fr is mu r, right? Mu, and R is mg cos theta, right? Am I correct? Please respond. No, is that big head? That's the person I'm even asking. I don't know that I asked the question. The rest of us got this, right? So by the time you do this, you are going to get that. Was it not what you did? Should we finish it? What's our mu? Okay, we have not even gotten mu. Mu is going to be tan theta. You see, I didn't even have to do anything. I just did tan. What's tan theta? 5'8". 577. Okay, we use 0.58 the other time. So 0.577 times mg, which is 400 cos 30 plus 400 sine 30. That's what? 200 is equal to F. So by the time you work this place, what are you going to get? Your answer will be something around 400 too, because this will be half times, you get it? That will be about 200 and something. Just work the maths. Let me see what you get. 0.5 times this times cos this plus 200. Huh? 399. 199.87 plus 200. It's not up to 400. That's approximately 400 basically. This will be 399.87, approximately 400. Well, yeah. Maybe we did not approximate here to give us exactly 400. Are we clear on that? All right, let's go to the next topic. The next topic is circular motion, right? Pause it. So basically, circular motion is just motion of a body in a circular path. And what is a circular path? Curve, linear, right? Yeah, curve. Do you understand? So, and the motion of a body in a circular path is not funny, but it's quite interesting, because when a body is moving in a circular path, have you ever ridden a merry-go-round before? Merry-go-round. That is that thing that you sit on. That one, that 3 foolish boys will sit on it. One foolish boy will not be the one to be pushing it there. So you're not enjoying. So you have ridden it before, okay? Or a roller coaster. Those ones that go in cyclic distance. You know, there's a force they put. If you have ever seen them, those are riding before. You see, they will push against the wall, right? Like against the wall of the distance, the chair, the back of the chair. To be like, right? So that feeling is because of a force that is known as centripetal force, torcative. Then there is a force. Okay, now a centripetal force, therefore, is the force that tries to pull the body towards the center of the towards that is trying to pull the body towards the center of rotation. Is that okay? But there's a force. That force that they will feel as if they want to pull away from this thing is a non-existent force that is called centrifugal force. Is that okay? That's what I wanted to bring out. That one is not centripetal, the one that pushes the body, that makes the body look like it wants to escape away. Is that okay? That one is centrifugal. But the one that directs the acceleration, and that's the point. In a circular motion, the acceleration of the body is always directed towards the center. The acceleration of the body is directed towards where? Towards the center. So if the body were moving like this, the acceleration will be directed towards the center all the time. Is that okay? So it is always such that the acceleration of the body and the velocity of the body are always perpendicular to each other. Get it? In a circular motion, acceleration and velocity are always what? So because the velocity of the body is always changing, so that's why the body has what? Acceleration. We call the acceleration centripetal acceleration. Why? Because we said it is always directed towards the what? Center. Centripetal. Center. Is that okay? Acceleration is directed towards the center. But what's the direction of velocity? Velocity is always directed in a direction that is always tangential to the whatever, to the what? Not whatever, right? To the what? Yes, to the path, to the circle at all points. Is that okay? So these tangents I'm drawing here, they are what? The direction of what? Of the velocity. Is that okay? And it's always changing per time. So the body is accelerating throughout. The body is what? Accelerating throughout. And the acceleration is directed towards the center. Okay. So the body is accelerating with, before I analyze, just get this, that the body is accelerating. I cannot begin to derive this because of, it's quite complex in fact. It's the acceleration that is equal to v squared over r. But of course, let's analyze the motion of the body. Now this body is moving in a circular path. Let's say the body started from here and move to this point. If it moved from here to here, we say it has moved an arc, right? And this arc will subtend a particular angle at the center, right? So we say that the speed of the body, so to say, is going to be what? We call it angular speed. Is that okay? Or angular velocity. Angular speed is going to be equal to the angle moved per time. Does this make sense? Does this make sense? Okay. Another thing you should know is that this so this is the angle, right? I wanted to also say something that the angular distance is given by the product of this radius. Listen, it's very simple. The angular distance, this distance in angle, is going to be the product of this radius. The radius swept through the entire distance, right? Or through this entire angle. So it's going to be theta times r. Does this make sense to you too? You've been given this in maths before. You don't understand this? You don't understand it. But do you understand that I just explained? You don't understand. See, if I call this place length, I call this place breadth, what will be the area of this thing? The area will just be the length times the whole breadth. Do you understand? This length throughout this entire breadth times breadth. Does that make sense? So here too, the angular distance, this angular distance here is going to be, and notice the angular distance is everywhere here. Is that okay? So it's going to be this radius that swept through the entire angle times the angle. Does that make sense now? Okay. So it means that we can also say that theta is equal to S over R. Does that make sense? I mean, but we really don't need this. This is what we need here. So omega is going to be theta over T. Does this make sense? So let's call this our equation 1. I'm just saying in case you have something to solve with this too. That's why I brought this in. Now you see, what do we need here? What if the guy moved from this place back to this place? It has moved the entire circle, right? It has moved the entire circle. So omega there will have what? 2 pi over T. Does this make sense? Equation 2. But this time T will not be just T, because it has converted a complete circle to what? Period. Does that make sense? Okay. Another formula you should know is that period from our wave, do you remember, is inverse of, so it means that this omega can also be what? 2 pi f. Does this make sense? Okay. Now, another thing is that you know that we said that this acceleration is change in velocity over time. Does this make sense? Now, angular velocity is also given by the formula v over r. This is also another formula. Angular velocity is actual velocity over, or centripetal velocity over r. Now, this is one formula. So we can invent stuff here. How can we invent here? There's nothing. Huh? WT over, where's WT? Okay, yeah. We can invent stuff here. So here it means that velocity will be equal to what? Omega r. Does this make sense? Are you looking at me? Equation 3, equation 4, equation 5, equation 6. Let's just generate all the equation we need for calculation. Are you getting it? So from here, you can also say that since A is V squared over R and V is omega R, so that will be omega R, omega squared R squared. Does that make sense? Are you with me? V is squared there and V is omega R. So omega is not W, this is omega here. Alright, you cover one side of the W. So A equal to over R in this case, right? So this takes care of 1. So A is also equal to R omega squared. Does that make sense? Equation 7. Another thing we now use is now centripetal force. So what is now the magnitude of the force? Force is mass times acceleration, right? We have said centripetal force is the force that pushes the body, that directs the body towards the center, right? Okay, there's always pulling the body towards the center. But the fictional force, fiction, that is the fictitious force that does not exist, fictitious rather, force that does not exist, which is the one the body will feel. It's as if it wants to escape, right? Actually, if this body moves, There's a question like that. If the body moves in a circular path, where will the acceleration be? Where will it move towards? To be directed towards what? A direction that is tangential to the circular path. If this body was being swung like this, or swung like this, are you listening to me? And it breaks off, how will it move? And let's say it gets out from this point. Where will it move? What do you mean like this? It will move in a path that is tangential. The tangent at that point is the tangent, is the side at which it will fling out. Is it clear? Are you sure? Okay. So if that body moves like this, in this case, and however, I saw a video somewhere on YouTube one time. A man tried to prove that that is not true. That a body that is in a circular path, when it gets flung out, it doesn't move in a tangent. But for your jam, you should know that it moves in what? A direction that is what? Tangential. But actually, I think it works because I've tried that thing one day before. And when that thing escaped, it will move in a straight line that is tangential to the point where it got released from. Do you get it? All right. So my point, the body that the force that the body will feel, that is fictitious, I said is what? Centrifugal, right? Okay. And it doesn't exist. The force doesn't exist. But the force, centripetal force in this case, is going to be MA. And A is what? RW squared. So that will be MR the omega squared, right? Equation 8. F is also equal to what? NA is TV squared, MV squared over R. This is the most common one. All right. So these are the major forces that we are going to be using to analyze this guy. Let's make it 10. Which other one can we put here? From there, right? Let's not complicate matters. Is that okay? Okay, there's another formula here. I'm seeing one here. T equal to period is, so what will period be here? 2 pi over omega here. And what will F be? Omega over 2 pi. Just the inverse of that. Does that make sense? Okay. So let's have some questions. Are we ready?
What of this A equals
A equals omega over T. Omega will be. And I tried to derive something there, but there was nothing that came out of it. So let's just leave it. Is that okay? But you understand what I did, right? That's angular velocity over time now. That's acceleration. Change of velocity over time. Right. Okay. So let's solve this question. There are many simple questions. They are very simple. Let's get one from here. Pause. S become what? U plus O. Okay, you don't even play it. You just played it, right? Oh. But like the mic was off. So you not hear anything there. Alright. U plus V over 2 times T, which is now V minus U over A. Okay, by the time you multiply this, difference of 2 squares, isn't it? So S will be equal to U squared minus V squared. Difference of 2 squares, it could be V minus U too. Because look here, the arrangement is not correct, it's not ordinate. This is V minus U, so let it be V plus U here. V plus U is also U plus V, right? Okay, so it is now V squared minus U squared all over 2A. The time you could multiply, V squared minus U squared is equal to 2AS. V squared is equal to U squared plus 2AS. Does this make sense? Alright, so these are all the formulas that we need, or majority of the formulas that we need. Now, another thing we might need them for is calculating with the velocity time graph, distance time graph, and all those things. And let's see some questions. Okay, this is what we'll do. Let me write some questions on the board and we'll solve them. Are we good? Okay. Okay, we also do artwood. Let's quickly do small artwood. We'll not do too much artwood, just small. Is that okay? You don't know artwood. It was under the last topic, so let's combine all of them so that I've seen questions to get that are under the same this thing now. So are you with me? Let's do a very simple one. A very simple artwood. Artwood is a system of two guys in a pulley. Is that okay? Held together by a pulley. So, this is a common artwood. But I've released a video on the full artwood, so maybe I'll link it in the description. I'm very discouraged. Let's call this M1 and let's call this M2. The force will be acting here, which will be called what? Tension, right? There's always tension in this string. Tension is always acting in the opposite direction to weight, where anything called weight will act. Mg sin theta will act here, right? Do you remember that? So the force that is acting against it is T. Weight will act downward here. Do you remember that? See, first analyze all the body. We call it free body. You can draw it. You can draw free body for this system. There's a force acting here, which is tension. There's a force acting here, which is mg sin theta. This free body is drawn with respect to this plane now. Okay? Now the other free body for this M2, this M1. The free body for this M2 is there's a force acting upward, there's a force acting downward. Which one is acting downward? Weight, which is M2G. Does this make sense? Are you with me first? Is anybody confused? Analyze all the forces acting on it first. Then the force acting upward with what? Tension. Tension always acts when there is string. As far as you see string there, rope there, tension must act. Is that okay? Tension must act. And tension almost always acts, in fact, always acts against the direction of weight. So if I'm suspending this body, if this my hand were to be a string, tension is acting upward, this weight is acting downward. So this is what you now do. So generate the acceleration of this system. Very simple. All the forces that are acting in direction of the motion, they will be positive, just the same way we did the last one. And all the forces acting against the direction of motion, they will be what? Negative. I'm showing you this quickly because we want to solve a question. Is that okay? So see this. Now, if in this case you are told that M1, this will be M1 sin theta. If M1 was greater than M2, where would this system move? This direction, right? But if M2 was greater than M1, where would this force move? So let's analyze the two cases. In the first case, M1 is greater than M2. If M1 is greater than M2, this whole thing will move in this direction. With which acceleration? That's what we want to get. Is that okay? Now, with which acceleration? This is what we'll do. The forces acting in direction of motion are positive. Forces acting against direction of motion are what? Negative. So for this guy here, the sum of forces are going to be, this one is in direction of motion, so m1g sine theta will be what? Positive. Does that make sense? Tension is in that direction, so it's what? Negative, right? So minus T is equal to MA. Because M1A for body M, for body M1, equation 1. If you don't understand this, raise your hand. For what we did the last time, is this clear? Are you sure? Okay. For body 2, there is a tension acting upward too. In this place, tension is acting upward, and upward is the direction of motion too, right? You are not looking at the board. There is a force acting upward, which is what? Tension here, right? Is tension in direction of motion or against direction of motion?
In direction of motion.
In direction of motion, right? So tension is positive. Is weight in direction of motion or against direction of motion? Against. So minus mg is equal to, but this time m2g, right? That's with respect to body m, body m2, m2a. Does this make sense? Okay. So it means that in this case here, tension is here, tension is here. We might not be giving tension in the string. So let's generate an equation for tension. So this is equation 2. So let's generate equation 3. Tension here will be equal to, we take tension there, equal to m1g sine theta minus m1a. Does that make sense? Okay. In this case, this guy will just go there. Tension will be equal to, this equation 3. Tension will be equal to what here? m2a plus m2g. Is this clear? Okay. So since tension is tension here, then both of them must be equal, right? So m1g, equation 4. So now say equation 3 is equal to equation 4. So m1g sine theta minus m1a will be equal to m2a plus m2g. Okay? So m1 is common. m1 into bracket g sine theta minus m minus a. Okay, it's the acceleration we want to get. Let's collect the guys that have acceleration together. So these guys have acceleration, right? So let's bring this guy here and bring this guy here. Does that make sense? m1g sine theta. Please follow me. Oh. Is it minus m2g is equal to m2a, everybody, plus m1a. So what will acceleration be here? Or we just say collect like terms, a into bracket m2 plus m1. So we now have m1g sine theta here minus m2g divided both sides by m2 plus m1. This takes care of this, m2 plus m1. So a is equal to m1g sine theta minus m2g over m2 plus m1. This will be the equation used to solve for the acceleration of this system. Very simple. Is that okay? All right. So now let's solve a question. So I'm going to write like 3 questions on the board, or 4 questions. They will come from both this place and this place. Are we done copying?
Yes, sir.
You say, please wait. Then wait, sir. That there is 2 kg suspended here or hanging from this side, 3 kg hanging from this side, and we have an angle 30 degrees between them. So there's going to be tension in this direction and tension in this direction. This entire system will move down, right? This entire system will move down, right? So forces that are in direction of motion, positive. Forces against direction of motion, negative. So tension is up for this body. Let's start from this body. Let's call this our M1. For this body, weight is in direction of motion, right? So weight is positive. Now, what will be in negative direction? Tension will equal to M1A, right? Okay, so weight here is going to be M1G minus tension is equal to M1A, equation 1. For this guy, so tension here is going to be what? Since we know what we want to do. Tension here will now be, I hope you understand what I did there. Are you sure? Okay, tension here will be equal to what? M1A minus M1G, isn't it? No, M1G minus M1A. Am I correct now? Okay. So For the next body, tension is in this direction, which is direction of motion. So tension is positive. Weight, mg sine theta. That's why it's acting downward, right? m2g sine theta. So minus m2g sine theta, because it's negative. m2a will be equal to the acceleration on a, on m2. So tension here will be equal to m2a plus m2g sine theta is equal to what? m2a. Sorry, what am I doing? Tension is tension, right? So m1g minus m1a is equal to m2a plus m2g sine theta. Are we here? So AA, let's collect them together. Let's say I come here. M1G. My idea is to make this guy positive. So that's why I'm taking this guy and bringing this guy here. So M1G minus M2G sine theta is equal to what? M2A plus M1. So M1G minus M2G sine theta. You are still with me, right? M2 plus M1. Then you now be asking, Master, is this all the formula will generate by this? See, this system, this is always the formula. Is that okay? Okay, so A is going to be what? M1. What is our M1? 3 times G, 10, 30, minus M2, 2 times 10, 20, sine theta, sine 30, over M1, M2, 5. Okay, but I'm not giving G, right? So 2G, 3G, 2G. Does that make sense? They didn't ask us to take G for 10 meters per second now. So A becomes 2G, half of this. 2G sine theta is going to be 1G, which is G, right? So 3G minus G. Are you with me at all? Equal to 2G over 5. Is it clear? Was that what you did? All right, number 2. Number 2 says, a fruit drops. Number 2 says, a fruit drops from the top of a tree 2 meters tall. The time taken for the fruit. Now listen, you remember this equation? This one I'm going to give you is very, very easy. See, whenever you have this system, how many, this motion in 2 dimensions that's supposed to be, right? Projectile motion is motion in 2 dimensions, right? The first dimension and the second dimension. First dimension up and down, right? Whenever you're analyzing motion in 2 dimensions like this, and you want to use this equation represents, this one here represents the horizontal motion. This one represents what? The vertical motion. Is it clear? Alright. So we'll change, how do we convert it to vertical? We'll just change this one to G. So whenever you're using this, you are giving something like this. From the top of a tree, if this was a tree, if this was our tree, then it means that our guy is just undergoing one dimensional motion. 1D motion, right? So what does that mean? It means that we can easily use this side. Is that okay? So let's go to 1 over 2 GT squared. But this time it's coming down, right? H, God bless you, will equal to this. Does that make sense now? So what is now H here? 20 meters is equal to 1 over 2 times 10 times T squared. Here 5, here 1, here 4. T squared equal to square root of 4. Does that make sense? T equals 2 seconds. Is that clear? Is it hard? Did the brother get it? Did you get it? And but like, do you understand what I did? This one, if you say the body move, use this. If the body is moving up and down alone, just up and down alone, it's not moving forward or it's not having any horizontal displacement. Just use this side of the equation. Does that make sense? And the next one, a car starts from rest. Let's go. A car starts from rest, moves with a uniform acceleration of 6 meters squared. So A is equal to 6 meters per second squared. It starts from rest, so U equals 0. Does that make sense? Starts from rest, U is 0. Acceleration is that. The distance it covers in the 4th second. So what does 4th second mean? It means that travels from 3 seconds. Then the distance moves from that 3 seconds to the 4th second. Does that make sense now? So we are just analyzing if this was, so if we have something against time now, velocity against time now, 1, 2, 3, 4. The distance we are calculating for is the distance moved from here to here. Does that make sense? Does that make sense? How do we do that? Just calculate distance moved from here, calculate distance moved here, you subtract it. This is what I just did. All right. So how do we calculate distance now? We use this, right? So S equal to UT, U is 0. So this one is sharper, this one is faster. Half A, which is 6 times T squared. What's T? So in the first case, third second. Are you with me at all? He said calculate distance with 4th second. You understand this analysis, right? Okay. So that will be 3 here, 1 here, 2, 3. 3 by 3, 9. S equals 9 meters. Is this clear? 3 squared, sorry. How is it 3 squared? How now? Okay, sorry. Thank you. Yes, thank you. 27 meters. Okay. In the 4 seconds, S is going to be what? Half times 6 times T squared now is what? 4 times 16. Thank you. Here 8 equals 48. So you now subtract them. 48 minus this. 1, 2, 21 meters. Is that okay? This is the distance moved in the 4th second. Is that clear? Then this one here is the simplest. Is the what? So just watch as I will analyze the entire thing. A truck, are you with me? A truck which accelerates uniformly from rest. Oh, sorry. I tried to shift it up, that was what resulted in. Acceleration from rest at the rate of 2 meters per second. So here is 2 meters per second squared. Is that okay? So U is 0, A is 2 meters per second squared. For 10 seconds. So here the time is 10 seconds. So this is the phase of acceleration. Acceleration, when you have a velocity time graph, the acceleration phase is the phase where there is a slant. The phase where there is horizontal distance is a phase of no acceleration, 0 acceleration, but uniform velocity. Then the next phase that there is slant is also an acceleration, but this time opposite acceleration, that is deceleration or retardation. Okay, so V here is equal to U plus AT, and T is 10. T is 10 seconds. So the velocity attained is going to be A times T, that's 2 times 10. This is what? 20 meters per second. So here, this place is 20 meters per second. It now says, maintains a steady velocity for 30 seconds. This steady velocity maintains it for 30 seconds. So 30 plus this is what? 40 seconds. Does that make sense? Are you clear on that? For 30 seconds. So this steady velocity that is maintained is for 30 seconds. Is it clear? I said, read what it says. Maintaining a what? Steady velocity for... So, where is steady velocity? From here to here, steady velocity. Velocity is not change. If velocity change, I said to the acceleration now, since acceleration is change in velocity over time, right? So you see a slant or a slant. This one is opposite acceleration, retardation. This one is positive acceleration. So here, no change in velocity or speed, so it's going to be uniform. So we say steady. Steady velocity for 30 seconds. So 30 seconds is the time over which is maintaining it. So from 10 seconds to move to 40 seconds. So at 40 seconds is when it gets here. Does that make sense? Okay? And it's then brought to rest in 5 seconds. So it's brought to rest in 5 seconds. So 5 plus this is what? 45. Does that make sense now? Okay? The total distance traveled is what? Very simple. So total distance travel. One thing you should know is that the area under a VT curve is equal to total distance. The area under a VT curve is what? So the area of all these shapes will give us the total distance traveled. Does that make sense? So we have this triangle plus, let me just draw this shape out so you understand what I mean. This is what I'm doing. So if we take the area of everything here, we are going to get our answer. So from here to here is what? 20. From here to here, 20. From here to here, 30. Isn't it? From here to here, 10. From here to here, 5. From here to here, 20. Is it clear? Let's see here. 30 because 10 minus. Good. So area of this guy what? Half base times height. Half times 10 times 20. Plus length times breadth. Let me write the formula so that you know. Half base times height plus length times breadth plus half base times height. So this becomes 1 over 2 times 10 times 20 plus 30 times 20 plus 1 over 2 times 20 times 5. Here 10. Here 600. 600 now. 750. I wonder how you didn't get this. No, you first said 650. Why? You have to be precise, accurate, sharp, on point. Do you understand now? Please, please. Next one. A ball is thrown vertically upward from the ground with an initial velocity of this. The maximum height reached is what? Very simply. Now, if you remember in our equation of this one is even simple. You are looking for maximum height reached, right? You can just use that since it's one path. It's only one path we are analyzing, right? And remember I said for this equation, whenever you are analyzing one path, you can use this guy, this side, right? So H, are you with me?
Yes,
for horizontal, you can use only this side. For vertical, you can use this side. Half GT square. But G here will be negative, yes? We're not giving time, right? Okay. That's very good of you. Do you know what we now do, Time equal to, You can use V square equal to U squared plus 2AS. This time 2GH, right? Okay. So G because acceleration due to gravity, H because of the horizontal distance. U is what? Initial velocity 20, V is 0, right? Because by the time it gets up, when it gets to maximum height, V what? It will not move again now. So V will be 0. So 0 equal to, so this guy was negative because it's going up, so it will be positive here. So 2GH is equal to U squared. Does this make sense? Okay. So H will now be equal to U squared, which is 20 squared over 2 times 10. 2 times G. Does this make sense? Okay, 20, the answer is 20 meters. Is this clear? Is it clear? Alright, let's write the next topic. Vectors and scalars. Right. First, let me clean the book. Alright, so we are on vectors and scalars, resultant forces, equilibrants, resultant forces and equilibrants, forces in equilibrium, and moments of force. Is that okay? Are we ready? Okay, so what is a vector? A vector is a quantity that has what? Magnitude and direction. Then what is a scalar? Is a quantity that has what? Magnitude, but no direction. Now, usually they ask which one is vector, which one is scalar. So let me give you a list of forces of quantities now. And now these ones I want to give you are going to be all vectors. The rest that you see in your exam will be scalar. So let's use the mnemonic M, F, M. Let's write it down. M, F, M, V, W, the what gem. MFM, the what? MFM, the what? Gem. The what gem? The what? Maybe GEM. Should we make it that way? GWEM. The what gem? MFM, the what gem? MFM, Volkswagen. Like Volkswagen, right? Shut up. I like that one. The what gym, right? Right? Volkswagen. Yeah, that Wajem. I like that one. MFM vet Wajem. Okay, our first M here, what? Moment. Second M, momentum. Is that okay? Third M, last M, magnetic field intensity, right? Magnetic field intensity or magnetic field strength. Is that okay? Or magnetic flux density. That's another name for it, right? Magnetic flux density. These are the three names for that guy. Just B field, that's what I'm referring to, right? B vector. Then F what? Force. Okay. V is what? Velocity. E is what? Electric field. This is the electric field intensity. So electric field potential will be what? Scalar. Electric field potential energy will be what? Scalar. T here will be thrust. Moment or torque here. Is that okay? So this one will be thrust. This one will be weight. Is that okay? This one will be acceleration. This one will be G. Acceleration is gravity. You don't have this in V. Gravitational force is a force. G. The word G. What is G again? Anyways, then E here what? Huh? Gravitational force, right? Gravitational force, electric field intensity, electric field strength, so they are the same, right? So it means the mnemonic and electric field strength. So it has to be, in fact, T squared. So it will be MFM V T squared or get what? Vem what? This M. Where will M be? Vem what? Is that okay? MFM Vem what? But this what will be T squared. So we have thrust and tension. No, thrust is not tension now. Thrust is force inside fluid.
It is actually writing T.
These are writing T, God bless you. So this M is what? Magnetic field strength or magnetic field intensity, moment or torque, force. Okay, let's go. MFM vet what? Sorry. MFM ve what? MFM vem what?
MFM then what?
M for moment or torque. M for moment or torque. F for force. M for momentum. Velocity. Electric field intensity. Magnetic field intensity. O strength. Magnetic flux density. W weight. A acceleration. T for thrust and tension. We're very poor today. Yeah, I think I know that. I wanted to make a song. You know, when we make song. Where are we? Are you there? So other guys, including pressure, including energy, anything energy is what? Okay. So oh good. Work done, area volume density, impulse power, mass, temperature, distance, displacement. So MFM, DMFM, God bless you. DMFM, them what? Is that okay? Displacement. Don't forget to please. So these are mnemonic for vectors. Any other one you see in your exam that is not here is going to be what? Scalar. It's going to be what? Scalar. All right. How do we resolve vectors? Now, I don't know if that vector usually comes. This vectors, IJK vectors. It doesn't usually come, right? Okay, so let's do. No, we're not doing it. Let's do resultant forces. Is that okay? Resultant and equilibrium. So let's first start with how do you resolve forces? If I have what's induction? If I have forces like this, F1, F2, F3, F4. If I have something like this, and this is theta 1, theta 2, now let's make some theta 1, theta 2, theta 3, theta 4. How do we resolve forces like this? Now, when we want to resolve forces or vectors, because force is a vector, so we resolve. We say so when we resolve vectors, we say we are resolving forces. Is that okay? All right. So to resolve this force now, we resolve in two dimensions. Is that okay? We have the vertical dimension. We call it vertical components. Is that okay? And we resolve the horizontal component. Okay. So and all forces here have both vertical and horizontal components. Is that okay? So let's draw it like this. A table. So we have the y component or vertical component. We have the x component of each force. So remember I told you if you are closing an angle, you use cos of that angle. If you are opening an angle, you use sine of that angle. Is that okay? So let's begin with F1 force now. One thing we can do here is to bring this guy here down. Is that okay? So that we have our reference points. Is that okay? So we want to resolve F1 in the vertical component. What? We have positive y direction, positive x direction, negative x direction, negative y direction. Is that clear to us first? Okay. If you want to resolve y in the F1 in the y component, will it be resolved to the positive y direction or the negative y direction? Negative y direction, right? So C is going to be minus F1. Now, with respect to this theta 1, are we opening the angle by resolving this guy here, or we are closing the angle? Opening, right? So it will be minus F1 sine theta 1. Does that make sense? Is it clear?
Yes, sir.
Okay. If you want to resolve this guy, this same F1 to the x component, it's what? Minus again still because it's in this direction. Minus F1 here, cos theta 1. Is that clear? Okay. For the next guy, F2. F2 already is in the y component, right? Since F2 is in the y component, this is 90 degrees, so we don't need theta 2. Does that make sense? So F2 is in y direction. So what you just do is come on under the y component and write what? F2. In the x component, is F2 in the any x component? So we just write 0. Does that make sense? It's simple. The answer is actually that we resolve this F2 in this direction. We opened it up to y component. So it became F2 sine 90. And sine 90 is what? 1. So it becomes F2. Then this one, we are resolving it to the x component. We are resolving to the x component. It becomes cos 90, and cos 90 is what? 0. Is it clear? Okay. Now the next guy, F3. F3 to y component. F3 to y component will become what? Positive now, right? What will it become U? F3. Yeah, it will not be F3 what? This F3, resolve it to the Y component. Cos what? Cos which theta? Theta 3, God bless you, because we are closing on theta 3. Or, so this is the same. F3 cos theta 3. Or F3 opening sine theta 4. We'll get the same answer. If you are not clear, raise your hand. If you are resolving to the Y component, sine theta 4 cos theta 3. Okay, let's now resolve to the X component as well. To what? F3 sine theta 3 or F3 cos theta 4. Please don't forget the minus sign if there will be minus. Don't forget it, because if you did not put minus anywhere, it will disturb your answer. Okay, now the last force, the F4. How do we resolve it? It's on only x-axis, right? So we just come in F4, positive x-axis. Now here, this guy is on positive y-axis, okay. Because if it was on negative x-axis, we have to put the minus there. Is that okay? It's not on any y-axis, so we have 0 here. Then this is, so summation of all forces in y-axis, and yes, theta 4. Therefore, is exactly on x component, so you don't resolve it anyway. Is that okay? Are you with me? It's exactly on that straight line. Once it's exactly on the horizontal component, resolve it on only x component, put 0 on y component. It's only on y component as we have this. Resolve it on only y component, put 0 on x component. Is that clear? So by the time you do your summation of whatever, let's say this was minus 4 sine 30. That will be minus 2. You put minus 2 here. Let's say it was 9 Newton. 9 Newton here. You now add everything together. You put your answer here. Then summation of f on x components for what? You get your answer. So is that okay? Yeah. Good. Now listen. The resultant force will now be this. The resultant of all of these forces acting at a point. Now all of these forces are said to be concurrent. They are said to what? Concurrent forces are forces that act on the same, at the same point. Is that okay? You also say at the same time. So they are concurrent forces. So this resultant force, so we say F resultant is going to be the square root of summation F sub y all squared plus summation F sub x all squared. Is this clear? Alright, then the direction of that, the direction of those two forces is simple. How do we get direction? If this is F sub y, summation F sub y, and this summation F sub x, direction of what? Tan theta. Is that okay? Direction of force of F sub r will be equal to tan theta, or summation F sub y over what? Summation F sub x. Is that clear? Sure. Are we good? Alright. So now, what if we wanted to resolve forces that were the resultant of forces in a triangle? So then we have triangular law of vectors. We use it for that. Now, right, triangular law of vectors. If two axes, no, let me, you already know it, right? So let me just state it. So if two sides of a triangle are represented in magnitude and direction. Should I continue it? If the two sides of a triangle are represented in magnitude and direction, so this is represented in magnitude and direction, the resultant is the third line that joins the 2 points together. Is that okay? That's the resultant. So that is for that. Then we also have parallelogram law of vectors. I'm going to show you how we use all of them. Parallelogram law of vectors says that if the two sides of a parallelogram too are represented in magnitude and direction, the resultant of this force is going to be the diagonal that is drawn. So if you draw this, then we can have this extension here. Is that okay? The diagonal that joins, the diagonal that cuts through it is going to be the resultant of the. Is that okay? This will be the resultant here, this will be the resultant here. Does that make sense? So here, I'm going to show you the formulas we use. For this one, we can easily use what? R squared is equal to what? Summation Fy here, summation F squared, which was what we used there. Does that make sense? So resultant here is going to be summation Fy squared, or just Fy, because it might just be one force. These are for three forces. Does that make sense? Fy squared plus Fx squared. Is this clear? But the resultant for this one is going to be, let's say this was theta and this was phi. Now for this one you can use sine rule, you can use cosine rule. Is that okay? So what you want to do is this: if this was A, B and R, this will be side R. Is that okay for resultant? So it will become that R squared, this resultant will be equal to what? This side will be small b, right? This side will be small a. Are you with me? Okay, that will be a squared plus b squared minus 2ab cos r or cos theta. Do you remember this formula in mathematics? So this is what you use to get the resultant. Is it clear? But you also, usually they will give you these two angles. They will give you an angle here. So you use it to find this side using angle on a straight line. Is that okay? When you solve question, you see that. And the last one you should know is the Lami's theorem. No, also know that equilibrant is a resultant. The equilibrant is equal to the resultant in magnitude, but opposite in direction. Is that okay? Do we get it? So the equilibrant of this system now is these two portions of the parallelogram going like this, then the equilibrant will be the one that is acting in the opposite direction. Is that okay? And when we have systems like this, if they are in equilibrium, we equilibrate. Because, and how would they be in equilibrium? Because of the presence of the equilibrant, right? The equilibrium brings them to equilibrium. So we can use Lami's theorem to solve this. And I've showed you this before, right? So how do we use Lami's theorem? Now, and when do we use Lami's theorem? Lami's theorem is used when, first, the forces are concurrent, and of course, they are also, they are concurrent, they are in equilibrium. Of course, if they are like this, they are in equilibrium. You understand why, right? Then again, the other thing is, so that's about basically. So let me draw this system here now. You are going to see the way we'll do it. I'll show you different kind of forces that systems that can be asked to resolve. And I will show you what is called the types of equilibrium. Then before we go to momentum and moment of force. So I said for this guy, an equilibrant is this. Why this one will be a what? What will this be? Resultant. God bless you. Why this one will be what? Equilibrant. So if I have here, I call it theta 1. Here I have theta 2. Here I have theta 3. Now your systems, some systems will not be given to you like this. So you bring it to this form. Is that one clear? Okay. Now when you have your system like this, simply come and say, let's say this place was A, this place was B, this place was C. We just use sine rule. The Lami's theorem is just a modification of sine rule. Is that okay? So it will be that A, this side A over sine. Yes, sir. Yes, sir. Yes. You know I like the man. That's good. Okay. So A over sine what? The angle that this side is facing, A over sine theta 3 is equal to B over sine, Deborah, tell me. Sine what? B over sine what? The angle that this side is facing is what? Theta 1 is equal to C over sine theta 2. C over sine theta 2, A over sine theta 3, B over sine theta 1. Does that make sense? And then you solve. You see, it's not hard. It's very, very, all right, let's go, please. I don't know did what. Okay, then moment of forces. You should join them. How? Like this? Huh? I join this. Join this. Okay, now, yeah, that's, when we see question, you will know which one to use. You can use any one. And we'll solve questions, don't worry. In fact, okay, thank you. We're going to be solving a lot of questions on that. Basically, let's quickly just check moment so that we know the formulas combination that we're going to be using. Okay, so how about moment of force now? Now, for moment of force, now, moment is a force around a pivot. Is that okay? A force around a pivot. So, if I have, now it's just a form of equilibrium. So there are three types of equilibrium. We have the static equilibrium, dynamic equilibrium, and stable, static or stable equilibrium, dynamic equilibrium, and what? We have stable equilibrium, neutral equilibrium, neutral equilibrium. So neutral equilibrium, neutral equilibrium is this, and stable equilibrium is this. The typical example we use is a funnel. The funnel is standing like this on the ground. Will it move at all? It's in equilibrium. So this is stable equilibrium or static equilibrium. Then dynamic equilibrium is this. If I place the guy like this, what will it be doing? It will be going back and forth, right? This is dynamic equilibrium. This is what? Is it ready? No, funnel. You put the funnel like this. Ah, Jesus Christ. You understand? The funnel will be going back and forth, right? So this dynamic equilibrium. Then the neutral equilibrium. Neutral. You sure it's neutral equilibrium? Okay, this is neutral equilibrium. Like this is dynamic equilibrium. Yeah. Are you sure? Then unstable equilibrium now. Is this it? Yes. Oh, okay. Yes. Unstable. Is it now neutral? Okay. So this is unstable equilibrium, right? To be unstable because you have to set it where on the very flat of it, make sure it's before it stands, right? That's what I call it unstable equilibrium. Is that okay? And any little push can destabilize the equilibrium. Unlike stable equilibrium, you push it. Alright, so those are type of equilibrium. Now, if I set a system up in equilibrium like this, we usually use a meter rule such that I put a weight. Now, if I do not put any weight on the meter rule, the meter rule, the pivot, the fulcrum, is the point of its equilibrium, which is the 50 centimeter mark. Is that okay? At the 50 centimeter mark, if I suspend it with something, it should stand, it should stay. That's the point of no equilibrium. Now, if I now put a weight on one side, there's more weight on one side than the other, right? For me to locate the equilibrium point, I have to adjust it towards the load, right? Okay, so that's what we do in equilibrium, basically. Is that okay? All right. So if I have a force, F1 acting downward, we are starting with forces acting downward, and I have a force F2 acting downward, and the distance here is A, the distance from here to here is B. Are you with me? In this case, we say the sum of clockwise moments is equal to sum of anti-clockwise moments. Is that okay? First, what is moment? Moment is going to be what? Force times distance, isn't it? So, force in a particular direction here now. So in this case, we are talking about clockwise and anti-clockwise. Where is clockwise now? This is clockwise. Does that make sense? Where is anti-clockwise? This is anti-clockwise. Is that clear? Okay. So if it's clockwise moment, it means that F2 times distance. Distance is the distance from the meter rule. Is that okay? F2 times A will be equal to what? F1 times B. So we say sum of clockwise moments is equal to summation anti-clockwise. Is that okay? Anti-clockwise moment. So what's the clockwise moment again? F2A is equal to F1B. Does this make sense to all of us? Where A are distances away from this pivot. Is it clear? Okay. What if we now had a system like this? We had a system like this now. These are pivots or fulcrum. And there is weight acting upward here, weight acting downward here, weight acting downward here. The distance from here to here, so let's call this one F1, F2. If it's only mass you are giving, just multiply by acceleration due to gravity. Is that okay? F3. And of course, if you don't multiply, you still get the same answer. Do you know? Because it cancels out on either side. Only that here might be the problem. Okay, it's not still a problem. It's not still a problem. Okay, so I said that this guy is the case. The distance from here to here. Let's call it here. Let's call it X. Let's call this one Y. Let's call this one Z. Are you with me? So, and you know that the sum of clockwise moment is equal to sum of anti-clockwise moments. For this one, with this force F1, will it be acting clockwise or anti-clockwise? Anti-clockwise, because you cannot come and resolve like this. Once you always resolve, you stop at this pivot. Is that okay? Yeah. So sum of anti-clockwise moment here. This one, will it be clockwise or anti-clockwise? Anti-clockwise too. No. You resolve this one clockwise. Sorry. You resolve towards the pivot. I'm sorry. You resolve towards the pivot. You are not coming like this. You are resolving towards the pivot. Yes, because this one is on top. Are you with me? If there was a force here, okay, now. Yeah, they will draw another system. So this force here will be resolved here. So that will be F1 clockwise now. F1 X plus, is there any other clockwise here? Yes. This one is also clockwise. Does that make sense? See. Right? F3 what here? F3Y will be equal to F2Z plus what? Nothing, right? Okay, so you use your formula and you're done. It's as simple as that. Oh. Is it clear? So what if the system now contained that one that I wanted to draw there? Let's say now add two forces, maybe even two forces here. One force here. Two forces here. One force here, right? One force here too. Two forces down, okay. If you have a scenario like this, the distances will be given. But usually they will give you maybe, they will not give you the entire distance. Is that okay? They tell you this is a meter rule, for example now. How many meters will be there? 1 meter. How many centimeters would that be? 100 centimeters, right? So, and they tell you something like, this is 35 centimeters away from this guy. What would this place be? Can you not calculate that? If this was actually, if they tell you that this was placed at the 50 centimeter mark, you can calculate how many will remain here. Does that make sense now? And if you're given this, you can also calculate. Okay. So now, if this distance here was said to be A, for example, and this place is X, from here to here is now X, and from here to here was B, or they tell you, okay, B. There are just many ways it can come. And from here to here, say it was Y. And from here to here, say it was C. And here to here, Z. I hope these sign symbols are not confusing you. They represent distances away from the pivot. Is that okay? Alright, let's call this one F1, F2, F3, F4, F5, F6. Very simply, clockwise moments. Now the one that are going clockwise, F1 times A plus X. Is this clear? Plus F2X. Does that make sense? Plus Because this one now is going to be anti-clockwise. Does that make sense? So we'll come here, the next one, F5Z. Does that make sense? Plus F6Z, Z plus C. Does that make sense now? So everything should be equal to F3Y, God bless you, plus F4B. So these are the possible 6 types of questions. Is it clear? Yeah. All right. So let's go to answering questions now. Should I draw all the questions on the board? So you start answering. Unlock the phone. Give it to me. Brilliant. Unlock the phone, please. Oh, okay, I have one here. Let me first start with this one. Okay, we have this. Okay, also, okay, I'm coming. This one is also very simple. It's the same. The only thing now is this: if this was X from here to here, and this was Y from here to here was Y, for example. What you do is, if this was maybe F1 and this is weight, sum of clockwise is going to be sum of anti-clockwise. So sum of clockwise is here. So this is clockwise, right? That will be weight X plus Y. Weight times X plus Y will be equal to what? F1 times X. If you are confused, raise your hand. This is anti-clockwise now, right? This is clockwise. Are we clear on that? Okay. All right. First, let me write questions. Okay, so now let's go to the first one. We have this system like this. There's usually a note that accompanies it. Is that okay? But I just remove the note so that we'll solve what we have to. We are told to find W here. Is that okay? So very simply, we don't have anything to do with anything here. It's rubbish. So we'll come here. This here, if we resolve this, towards here. We only resolve towards the pivot, remember. Is this clockwise or anti-clockwise? Clockwise. Just get drunk. Then the tension, resolve tension towards here. Is that clockwise or anti-clockwise? So that will be the tension 20 times, what's the distance? 1 meter will be equal to the weight times, what's the distance? 2. Was this what took you 30 minutes? Okay. 10 Newton, right? Am I correct? Let's go to number 2. Number 2 says, let me clean up this. Oh no, let's use it. Number 2 says, this place, clockwise, right? And this 2 anti-clockwise, right? So clockwise there will be 50 times 1.5 will be equal to that guy there. X times 1.5 plus 15 times 2. So this becomes 1.5 times, 15 times 2. So, I mean, we could, 15. If we multiply it by 10, that will be, it doesn't change it, right? As in my point is, if we multiply this, that will be 500 times 1.5. That is MGO weight. Is that okay? Is equal to X, which will be 10X times 1.5 plus 15, 150 times 2. If I divide through by 10, still have the same answer. You get it now? So this does not change it, right? Okay. Are you clear on what I just did? Okay. So 50 times this, 15 times 5, 75 is equal to X 1.5x plus 30 you subtract 45 is equal to 1.5x. Divide both sides by 1.5. So that will be 15, 450 here, 1 here, 30. So x is equal to 30 kg. And it means there is a mistake with the question if 30 kg is the answer. Do you understand? There's a mistake with the question. Maybe this place is not 1.5. You get what I'm saying? Alright. Because this is anti-clockwise, this is anti-clockwise over 3.5. There's not 3.5 from here to here. Okay, maybe the question was actually that from here to here was 2 meters. Just and so it's now be 3.5. You get it? Eh? Give you 15 kg. You know what that would mean? That would mean that this guy times 3. This guy times 3.5. This guy times 3.5. Solve it first. Use 3.5. Let's see. Let's go to number 3. Number 3 says a 90 centimeter uniform lever has a load of 30 suspended at 15 centimeters from one of its ends. So from here to here, 15 centimeters. The load is how many newtons? 30 newtons. So 30 newtons here. So from here to here is 15 centimeters. You can pick any end though. I'm just deciding to pick it. If the fulcrum is at the center of gravity, so what's the center of gravity here? 45, right? So 45 here, 45, 0.45 meters. Here will now be what? 0.15 meter. What force must be applied to the other end to keep it in horizontal equilibrium? So in this case, so from here to here that was 0.3 meters. Does that make sense? Is that clear? So this will be clockwise moment, right? Anti-clockwise moment now. To the other end. So anti-clockwise moment will come from here. Is that okay? So we'll say that clockwise is 30 times 0.3 is equal to
0.45. From the end. The first end to 0.45.
No, it's 30 times 0.3 is equal to, okay, this side, yes, the force times 0.45. So this becomes 3 times 3, 9 is equal to 0.45 F. Or 0.45 or 0.45. So 1, 2, 45 here, 1 here, 20. F equal to 20 Newton. Is it clear? Okay. So, and here F is the force that will be suspending here. Is that okay? So, and the force, our force here will mean it will be hanging, right? To be hanging here. So it has to be anti-clockwise because it was standing to join clockwise. Did you get it? Because it might ask which direction should it be placed. Okay. Which one really gave you problem that I should just solve first? Everything now more like. So watch. How do we solve that? Very simple. What you want to do here? Are you with me? I said there's a point O here. What you want to do here is this. And here number 4. What you want to do here is this. You have to find the tension T, right? Okay. So here is tension T, right? Tension T is keeping it in equilibrium, right? Okay. So basically Let me see the question. Pause it, please. There's a note with the question, 13 meters.
Oh, you look
Why
like
did you multiply? Why did you multiply what? Yes. I'll give you the distance. No, we're not giving the distance. Here's the question. It says, where is it again? Okay. By a chord at that angle. Calculate the tension in the chord. If the horizontal are you okay? We don't have to be told. It's very simple. Listen, we don't have to be told that these things are the center. Do you know why? Because the highest weight of these things are at the center of gravity, right? So it's only at the middle here that it's what? 200 newtons. So here is 25 meters. Is that clear? So it has to be 200 times 25. 200 times 25. But do you understand this part here? Eh? First, let's resolve the force to be a standing force. So we now say that force will now take the anticlock, the moment of the force. Is that okay? So when we resolve it, to be t cos 60 times that. So first, let's divide by 50. Let's see what we have. We have 50. Here, 4. Right? So that will be 100 is equal to t cos 60. So 100 is equal to cos 60 what? Half, right? T over 2. T equals to 200. That's the answer. Is it clear? Alright. Oh, I hope it's not confusing. Okay. Let me show you this. Let's do this one. This next one says this. So this one is, we can use Lami's theorem here. No, we're not using Lami's theorem because what does the question say? It has a note where the note says that, it says in this diagram, MN is perpendicular to ON. That makes sense, right? And MP. MN is where ON and MP, yes. What is the difference between the moment about N of the force 20 applied along MP and the moment about O? Because it's very simple now. What's the difference? Moment. Okay, we didn't do moment. See. Moment about a point. For example, look at this question now. Look at this question. There's a force acting in this direction and the force acting in this direction. If you are asked to find the moment, the magnitude, this is a couple, is that okay? Couple is just two equal forces that are acting in opposite direction. So if we are asked to find the couple, just say, and this way is giving us 0.25 meters. First, the forces are equal. Is that okay? So the moment about here is going to be the moment about here. Is that okay? So the couple is going to be just 0.25 times 10, that's 2.5. Is that okay? Do you understand now? So that's what they want to bring out there too. A couple. It says, the question says that, what is the difference between the moment about n? So what do you see here? Couple, right? Do you see a couple here? So the moment about n, I mean, either way, n will fall here too if you alternate it. Because here will also be 0.3 and this distance here. Do you understand now? Very simple. So all you just do is calculate the distance here. How do you do that? That will be 0.5 all squared is equal minus 0.3 squared is equal to x squared. Well, you know what I did now? Pythagoras theorem. Is that clear? So this squared is equal to d squared plus d squared. So by the time you work it, what are you going to get? 0.5 squared is equal to 0.25 minus 0.09. What does it give you? 0.16, that will be 0.4, right? 0.4 meters. So by the time you take the moment about this, the couple, the moment about that end is going to be 0.4 meters times this guy. Is that okay? So that will be P, which is 20 times 0.4 will be equal to, so the difference here also will be what? 0.4. Is it clear? Are you sure?
Yes, sir.
If it is 0.4, this place will be 0.4. So the moment about it will be what? This times this 2. If you subtract it, you get 0. So the answer is 0. Is it clear? It says we should calculate the difference between the moment about n of this force along MP and its moment about O. Do you understand now? And its moment about O. The moment of this same force about O. Is that okay? O is also the same distance from it. So by the time you take the moment, it's going to be the same answer, 20 times 0.4. You subtract it, you get 0. Is that clear? All right. Then the next one, now this one uses Harmonic theorem. So, and it's not Adida. Are we good? Are you tired? Never, right? Okay, so here, you can use Harmonic theorem here, right? If it is 30 degrees and it is 90 degrees, what will this whole place be? 120 granite, right? What will this be? 60 granite, right? So that everything here is what? 150 granite. Are we clear on that? So how do we find T1? We just say T1 over sine 150 is equal to what? The weight downwards over sine, weight over sine 120. If you don't understand what I did, I'm going to link the video of Harmonic theorem down in the description. So T1 is what we're looking for over sine. Sine 120 is the same as what? Sine 150 is the same as what? Sine 30. Right? ASTC. AS cast. Right? I'm correct, right? So sine is positive in second distance, second quadrant, and this second quadrant. So sine 30 is correct. Am I clear? Sine 30 is the same as sine 150 in second quadrant now. Are you with me? Sine 150, thank you. Is equal to W. What's our W there? 10 times 10 over sine 120 again, second quadrant is equal to sine 60. So by the time you work this, so you see what she did is correct. Sine 30 is equal to sine T1 sine 60. I'm going to show you two methods. So the second method was what I think she used. So in this case, we'll divide both sides by sine 60. And what is sine 60? 1 over root 3, right? And that's 0.866. So 0.5, that will be 50 divided by 0.866. What would that be? Can it be 57? 0.7 whatever Newton, right? Look at the second method. What? If you do not get that, just look at the second method. Now look at the forces. Where would this one be acting? This tension be acting? You know the direction is not given here. In what direction do you think it will be acting? In this direction. Where will this one be acting? Downward, right? So let's draw the forces. One is acting downward. The other is acting in this direction, right? So let's draw again. Downwards, sideways, and the other one is acting that way, right? So, is it clear? You see, it's simple. But this here is giving us 30. So we'll draw it just the same way it is given to us. This way is 30, right? To that force, isn't it? Are you with me? 30 granules. So what will this place be? 60 granules. This is T2. This is weight. This is T1. So what will this place be? 90. Alright, you can now solve as you like. So weight is going to be what? 100 Newton. So if I were you, I could just use to get this relative to this guy is adjacent and this guy is opposite, right? So I'll just say opposite. This guy is opposite, right? Opposite over adjacent is equal to tan theta. And what we have is tan 60. So we have tan 60 is equal to opposite, which is 100 over T1. By the time you do it, T1 will be equal to 100 over tan 60. What's tan 60? Divide it. 57.7. Are we clear? Is it hard? God bless you. Let's solve the last one. Which method do you prefer, Lami's or triangular or vector? Oh, I think I prefer that one. That one is okay. This one you have to draw. Okay, you say I'll give you a shape now. You see figure, you will run. And I want to solve it. Look at this now. Which one is that? Consider the three forces acting at point O and in equilibrium as shown above. Which of the following equations is or are right? This is just common sense. P1 cos theta, that is, you resolve it here, is equal to P1 cos theta 2. Nonsense, right? This one, P3 will be in equilibrium with, let's do that by ourselves. Why are we looking at it? P1 cos theta 1, if we resolve it here, plus P2 cos theta 2. Am I wrong? Does this make sense? We resolve this and resolve this here. They will be in equilibrium. Then the number 3, P1 sin theta. P1 sin theta 1. Sin theta 1, that is, I'm opening it here, right? P1 sin theta 1. And P2 sin theta 2. They will be equal, yes. Yes, now they will be in equilibrium now. Does that make sense too? So that's it. Aye. P2 cos theta 1. P2 cos theta 1 plus, it's supposed to be P2 cos theta 2, right? Plus P2 cos theta 2. Let's make sense of it though. First, this one I said P1 cos theta 1. Wait, let's be sure. P1 cos theta 1, that one makes sense. P2 cos theta, P1 cos theta 2. Let me see the question again. But that 3 is correct, right? And the options there, let me see the options there. The options are I only, I only, I only, I and I only, and I and I only. So, and the answer is D actually. The answer is D. D says I and I only. Maybe I didn't write this correctly. Oh, sorry. It's P1 cos theta 1. And what we have here. Okay, so both of them are correct. Does that make sense? Okay. Okay, do this one for me. Sorry. Well, the projectile is anything that you can launch, right? To undergo 2D motion. Motion in 2D, right? Vertical direction of it and horizontal dimension. Baba, you want to take over the office? Listen now, if I throw this body, water. If I throw this body, it comes back to meet me in that same place, right? There are many things we use. We are not solving questions. Sit. I just want to explain everything. So there are many things we use in the dimension, in the analysis. Is that okay? So first, the path that this projectile takes is called what? Trajectory. Is that okay? The path. Listen, if I throw this body now, it's going to move from this position. Is that okay? And come back to that same position. Is that okay? To come back to that same position. This path that it takes is called the trajectory of the moment, trajectory of the projectile. Is that okay? Now, this entire path. Now, there's something about it. First, we have a time of flight. First, no. This guy is going to change in velocity. As it's going up and coming down, right? As it's going up, what will happen to the velocity? Velocity will what? Decrease. Do you understand? Until you get to velocity will be 0. And as it's coming down, velocity will increase until it gets here, where it becomes maximum just before it touches the ground. Velocity becomes maximum just before it touches the ground. Okay. Now as it's going up, we've mentioned that. So it's going to have two components. The first component of the velocity is going to be what? The vertical component. What will the vertical component be? If here was theta, what will be the vertical component? Open, right? That is what? Sine. So that was u sine theta. So u in y component, what? U sine theta. U in x component, what? U cos theta. Is that okay? Okay. Now, so there are some this thing we use for analysis. Now we talk about the time of flight. Now there's something about this projectile motion. There's what we call time symmetry. What we call what? What does that mean? It means equality in the time it takes to reach this maximum position and the time it takes to come back to the original position. Does that make sense? So that's why we say the time of flight is given by 2 times of u sine theta over g. We got that from v equal to u plus at. Knowing that the time taken to reach maximum height is what? Okay, when you reach maximum height, what will be the velocity? 0, right? Equal to u. Now it's going up, that's minus gt, right? So gt by the time you come here equal to u, right? Are you with me? So what would time now be? Even my handwriting, I don't know. So t equal to u over what? G. So this will be the time taken to reach the maximum height. By the time, since the time, there will be time symmetry. Time taken to reach here is equal to time taken to come back here, right? So that will be the total time of flight is what? 2u over g. If we have theta to be 90 degrees. Is that okay? Well, where theta is not 90 degrees, u component will be uy here. And uy is what? U sine theta. So our formula of what? Total time of flight is what? 2u sine theta over g. Does that make sense? You see, I'm trying to rush because of it. Okay. So then there's also maximum height. At maximum height, we have what's the formula for maximum height? U squared sine squared theta over 2g. You know where we got that from too, right? Okay, so I don't need to check again, right? Okay. So that's maximum height. So if theta is 90 degree, are you with me? We'll have u squared over what? 2g. So you can also apply this formula. Then the other component that we will analyze is the total horizontal component, horizontal distance move. We call it range, right? The maximum range. What's the formula for maximum range? U squared sine 2 theta over g. Is it over g over 2g?
Over G.
Are you sure? Should we quickly derive it?
No. Right.
Now I'm going to link a video in the description where I derived everything. I used two methods. How many people have seen that video? Projectiles. If you want to understand projectiles, well, remind me to send it to the group. You've seen it. You watch everything. So this is the formula, right? All right. Where 9 theta is 9. Where so the maximum range will be reached when theta is what? 45 granules. Is that okay? So if I want my this thing to go the farthest distance, I have to position my hand at angle 45 degrees. Yes. What is granite? 45 degrees. So are we good with projectiles now? If I are done with projectile. Now let's go to SHM. SHM. Quickly, eh? See where I rushed it, eh? Somebody say SHM. SHM. Ha, Tulu. My vibe. SHM. See, you guys are lazy. You think I'm not tired? I've been the one talking since. I don't mind them. Baba slept. You now came and said, don't mind them. It's just any periodic motion. Is that okay? What physics use to describe it is motion of a spring. Is that okay? On which a load is applied, is attached. So if I have this string attached here, and then there's a load on this thing, and I cause this string to oscillate back and forth, what will happen is going to oscillate to its maximum stretch and its minimum stretch. Is that okay? Let's say its minimum stretch was around here, and our load is here, and its maximum stretch is around here. So it means that this thing is its equilibrium position. Is that okay? So from here to here is going to be its oscillation, point of oscillation. Is that okay? So we can call this x. Is that okay? From here to here, xx. Is that okay? Back and forth. At maximum point here, it's going to have highest potential energy. Is that okay? At maximum point here, also it's going to have highest what? Potential energy. Is equal to a system of pendulum. Is that okay? Where here, P will be what? Maximum. P will also what? Maximum. At this point, what will be maximum? KE. Do you understand now? So half mv squared is maximum here. Here. mgh is maximum here. Are you with me now? So for a system like this, we usually use, there are many things we use. First, you should also understand that this system works with works like the circular motion, and I've proven that before for you, that periodic motion creates what? Wave-like system too. Is that okay? Okay. No. Are you with me? You're with me, right? There's something I'm trying to even generate now. Now, with this guy, we know that this maximum potential energy is going to be maximum kinetic. It will be equal. Energy conversion is just taking place from here to here, right? At this point, potential energy, kinetic energy is only what this body has. No potential energy. Is that okay? Potential energy is 0 here. Kinetic energy is 0 here. But the values are equal. Am I clear? Yes. Okay. Now energy stored in this string. Energy stored in this string is going to be given by half kx squared. Is that okay? But of course, we also know that the force that is acting on it, let's not begin to analyze force here, because we have to do elasticity using Hooke's law. Hooke's law says that the force is proportional to the extension produced, but we're not going to get into that now. Is that okay? So let's go to kx. K is what? The spring constant, right? Okay. And we also know that its oscillation, the energy stored in the string, will be equal to the maximum kinetic energy. Maximum kinetic energy here, the maximum kinetic energy. Does that make sense? Our kinetic energy is half mv squared. That will be equal to what? Half kx squared. And the x here is going to be the oscillation. If it's oscillation, the maximum point is going to be the amplitude. Does that make sense? Okay. So we can say that half takes care of half, and mv squared is equal to what? Ka squared. So we can now say that let's look for velocity here. Velocity will be equal to what? Ka squared over m, right? Okay, so the square root of everything here. Does that make sense? Okay. Another thing we can bring out from this place is that this square cancels square root. No. Okay. That's good. In this case, right? So v here will be equal to root k dot root a squared over root m. So v here will be equal to a root k over root m. So it means that we have proven that the velocity of an oscillating body is directly proportional to the square root of the spring constant and inversely proportional to the mass of the mass attached to it. Is that okay? Good. Now let's talk about some other things about it, like the period of oscillation and all those things. You remember that period, if period is the time taken to complete one oscillation, right? So period here, are you with me? Period here can be equal to the circumference of the circle, which is what? Circumference, that's the total oscillation. Is that okay? Per velocity, per speed. Because remember that, do you remember this thing, 2 pi over, do you remember this thing, omega equal to 2 pi over something that we generated the other time? So from there, we know that period is also equal to this guy over velocity, right? Are you with me? So T equals, what's the circumference? Circumference is what? 2 pi r. And this time, our radius is going to be the amplitude. Does that make sense?
Yes, sir.
Okay. Are you sure? Okay, over v. What's our velocity? We got a root k over root f. So a takes care of k. So T is going to be equal to 2 pi. This guy will go up. Root n over k. Does this make sense now?
Yes.
All right. So experimentally, it was also determined that T is directly proportional to the square root of length over square root of g. So, am I correct?
Yes.
So then T was also found to be 1 over, what's that formula? 2 pi L root L over g. Do you remember this formula? Is this formula correct?
Yes.
Verify it.
Yes, sir.
Are we good?
Yes, sir.
Are we good?
Yes, sir.
Can we go?
Yes, sir.
Okay. So that's the formula for period. So what will now be the formula from here? What will be the formula for frequency? Generate that and put it in the comment section. All right. That will be for the first segment of our 5 days of physics. In the next segment tomorrow, we'll continue on the second day. God bless you as you subscribe to the channel and share the video with your friends.